Alright, so I wanted to demonstrate something with conic sections. It becomes very apparent with parabolas. So here I have a classical mathematical cone here, the double-lobed, two-lobed cone. Right? So you've got what you would expect to be a cone, but then there's another one on top of it, right? Basically, like, each of the lines is just each of the line segments that forms the surface of the cone just extends infinitely. So you get a double cone. In a sense, this makes sense, right? And I've turned off perspective for a reason. Have it that way. There we go. Okay. So now this is a three-dimensional object, so it exists in a space with three axes. There's one that goes down the cones. So this is the axis of symmetry of the cones. And then there are two perpendicular axes. So we might say that the axis of the cone is the real axis. The other two, we're not considering anything to happen. Those are our imaginary axes, right? So maybe we're considering this in terms of quaternions or octonions or something, right? So these other two I've labeled I and J. So there's I, that one right there. There's J. Doesn't really matter. As far as the cone is concerned, they're the same thing. They're both just perpendicular to the cone. Now, say we want to take a conic section. We want to take a cross section of this guy. And what we want to do specifically is we want to take a parabola. Right? So what we're going to do is we're going to cut it with a plane, and that plane is going to be parallel with one of these, the side somewhere along there, because there's an infinite number of choices to choose from, right? Because it's, well, here there isn't. There's like 32 or something. But on an ideal, actual, perfect cone, I wonder if I can smooth this. Can I smooth this? No? Doesn't care? Wait. So now that looks worse. Anyway, yeah, I'll just leave it as it is. So we're going to cut it with a plane, and you can see that I have that. It is set at the same angle as, there we go, deselect everything. It's set at the same angle as this, right here. It's set at 45 degrees. And I set it at 45 degrees for a very specific reason, which I'm actually not really going to get into at this point. But here it's set at 45. Any angle that it's set at, it doesn't really matter. Any angle that it's set at, that the cone is set at, that's going to be the angle of our plane that gives us a parabola. Right? And you can kind of see, get in there, you can kind of see that that's going to be a parabolic cross-section. I'm not real interested in actually taking that cross-section. I'm interested in talking about what happens when we do. What are the actual logical consequences of what's going on here? Okay? So now on this plane where we took this cross-section, we have a y-axis, right? So that is the axis of symmetry of the parabola, of that conic section. And it is in one plane, in this plane here created by, what is that? That's I. That's what I said. No, that's J. That's what I said J was. In the plane created by J and the real axis, which is the axis of the cones, Y is simply, depending on how you look at it, it's either just a line of the form f of x equals x plus something, plus c, whatever your intercept here is. Or, if we're on the other side, let's see, it's negative. It's f of x is negative x. Right? Either way, doesn't matter. But yeah, it's at a 45-degree angle to these other reference axes. Now, we want to also have, because this is a plane that we're using to cut this cone, we also need an x-axis. Okay, so there we go. And that x-axis is parallel to one of our three axes here. I think it's, is it, I keep getting it wrong. Okay, it's the one I have labeled I. Okay. You think I would remember that because this is leading up to something. Alright, so the I-axis, here's sort of your basic imaginary axis, is parallel to your x-axis. Right? Let me pull that plane out of there. So, oops. Helps if I click the right thing. Let me pull the plane out of there so it's easier to see. Okay? So this guy, your x-axis, this guy right there, is parallel to this guy across 3 space. It's parallel. They're completely parallel to each other. Okay? Now, when we take when we try to find roots of the parabola, let's see, let's bring the plane back. Okay, so when you try to take roots of the quadratic, the equation that yields the parabola, in this case, because, so see right here, we are up above the x-axis. We're up in the positive y's. So this parabola has no zeros. It has no quote-unquote real zeros, right? Well, this is interesting because what happens? What do you get for your roots? You get imaginary roots, imaginary zeros. Okay, but what does that mean? That means that your imaginary axis should be perpendicular to your y-axis. Okay, so just for a reminder, this is our y-axis right here, the one I'm blinking in and out. That's your y-axis. Just like your x-axis is perpendicular to it, this is your x-axis. Your imaginary axis has to be perpendicular to the y-axis. Its zero has to be this point here, this origin here, where we get J coming through, right there, where we get the x-axis going through, and where we get the y-axis going through. That point where everything is coinciding right there needs to be the origin of your imaginary axis, and it needs to be perpendicular to your y-axis, which is this one. Okay? So, this circle right here is going to be all of the possible directions we can go that are perpendicular to your y-axis. There's another rule here too, though. Your imaginary axis relative to y, your imaginary axis relative to y, needs to be perpendicular to the reference frame of the x-axis. Okay? The reference frame of the x-axis is what is established via the cone, the real axis, the y-axis, and the j-axis here. We need to be perpendicular to that system of axes. I don't know how else to say that. There's only one candidate for this, and that is the x-axis itself. That's the only one. Anything else will not be perpendicular to that entire complement of axes, right? It has to be perpendicular to this, to this axis, has to be perpendicular to this axis, has to be perpendicular to this axis, has to be perpendicular to this axis. Okay? There's only one candidate, and it's this axis. It doesn't actually have to be perpendicular to this axis. It has to be perpendicular to the entire rest of our reference frame. this sweep here indicates to us that there's only one option, and it's specifically this, which means when we're working with conic sections and you get imaginary solutions, they're actually the same as the real solutions, right? They plot on the same axis because that's how it works. Which means, so let's see, let's take this guy. Let's duplicate him, and then which way we want to rotate him on Y, -90. Which means basically that's what your imaginaries are actually interacting with. Notice, let's see, this axis here is imaginary relative to this axis. So what the imaginary solutions are actually telling you when you're taking conic sections is they're talking about the relationship between the axes of the cones that you're cutting, not the relationship between the dimensions that you're plotting in. Because the full cone, let's see, actually looks like this. There's 3 cones. There's 6 lobes to the cone, right? And what ends up happening here is we end up being able to ignore this one because of other reasons. There's other things that are occurring that we get to ignore this one for. This one's producing a hyperbola in this particular case, but we get to ignore that, and we're just gonna. But to actually get a parabola correctly, you do need both of these 2-lobed cones here. And once you have those, you get your imaginaries plotting on plotting on your plane just the same. And if you look at your complex solutions to the quadratic formula, the solutions that you get, if you actually just plotted them, give you a parabola for sure anyway. And it has to be perpendicular to, they have to be plotting perpendicular to the y-axis, but they don't have to be perpendicular to the x-axis, because the way the x-axis is actually defined in this whole system, it's not a basic axis. It's one which is generated from consequences of the interactions of all the other axes. And so the imaginary axis, where you would plot your imaginary solutions, your imaginary roots, is the same way. And it turns out that the entire system of axes gives you that this real plotting axis and this imaginary plotting axis are the same exact axis. So, yeah. And there's a very simple, I think, demonstration of this fact. There is no other possible alternative to this. This is the only thing that explains how it works. This is the only way that I think you can get to this. So